Right. Okay. So then right now we just spoke about what diffusive equations mean and what they look like, which is something we have been discussing for quite a while already. So then the other side of the equations, sorry, the yeah. So on the other hand, we have something which is known as convective equations. So what these convective equations are typically is what was the wave equation, which we discussed last week extensively. And we saw that in case of a wave equation, when we are trying to resolve it in terms of our knowns, that is when we are trying to discretize the equation by replacing the spatial derivatives by finite differences, we realize that not all schemes are suitable for the wave equation or for any equation for that matter. We have to look at something known as stability, we have to look at consistency, and also at convergence, which are related to each other. So that was the takeaway from whatever we were discussing earlier. So now this time we are delving a little bit more deep into all of these schemes that are available for us to solve the various equations. So the discussion was focused around the wave equation or an advective type equation. I hope we're clear with what means by advective type of equations. It's any equation in which the flow of a property plays an important role. So we had discussed earlier the example of if you have ink in a basin which is not having any velocity associated with it, that is, it's still water. So in that case, we saw how it is a diffusion oriented system. However, when we are dealing with a system in which there is a movement of a property, that is movement of flow, then whatever your properties at the various cells or various locations in your domain are going to be impacted by diffusion because of the concentration variables, such as if we are talking about ink, then of course diffusion is going to play an important role. That is, wherever there's more ink, it's going to have a tendency to spread to the areas with lesser ink. This ink example is something that I typically take for those who are joining for the first time. That is, we consider a trough, that is a basin in which there is some water, and if you put some ink in it, see, like straight in, then what will happen is that the ink will have a tendency to sort of diffuse over the entire basin. However, if you were looking at a river, for example, and then you throw a bucket of ink in here, so this ink will travel along with the flow, that is at t plus delta t at some time in the future. The whole region which is affected by the ink is going to move by a certain distance. This plus diffusion. So advection plus diffusion is what is happening for this example. Meanwhile, for an example in which there's no flow, only diffusion is happening. So that this is basically this is building up to the definition of transportiveness, which is important for us to categorize various schemes that we have, which we have to solve the equations, the wave equation or vector equations. So transportiveness is based on the direction of flow. That is, if there is a flow, then based on its direction, if you're looking at location P, which is some present location, and we're looking at the location E and W, which are at either side of P, then depending if the flow is moving in this direction or in this direction, there is going the property at P, at point P, is going to be more affected by um, wherever the flow is coming from. So, for example, if the flow is moving from W to E, then what is going to happen, that W is going to have a strong effect on the properties at P. Meanwhile, that effect will not be very strong at E. From the effect that is coming from E is not going to be very strong for P. Right. So in the absence of this convection, that is in the absence of any flow velocity, there is going to be only diffusion. So basically diffusion becomes less dominant for convective systems, but it does not go away. And the degree of dominance of diffusion depends upon the speed of the flow and also upon how fast the diffusion action is. specklet number, which is an important non-dimensional number, is a measure of the same. So it is a measure of whether diffusion is more dominant or convection is more dominant. So you can imagine that for flows which have a high velocity, you're going to have more dominance of convection as compared to diffusion, right? So then a lot of the discussion was based around the quick scheme in this particular week. So the quick scheme is basically quadratic upstream interpolation for convective kinematics. It's a lot of words, but basically what it means is that we are upwinding. That is, we are trying to enforce this physics that we have over here. Basically that there is more effect of flow from the property from one side in a flowing system than the other. We're trying to implement that in terms of our CFD mathematics, and that is called upstream interpolation, or basically it is called upwinding in more colloquial terms. This is for upwinding. Upwinding for convective kinematics. So basically when you're going to start developing your own solvers, so these whatever we are studying right now will make more sense. So right now it is a lot of random mathematics that you might find that we are trying to represent the same thing, that is derivatives, spatial derivatives, in different forms. But why we are doing that is each of these schemes have a different mathematical behavior which has real implications upon a solver. If we're trying to build a solver, then we want good mathematical behavior from whatever discretization schemes we are trying to take into account. Discretization, or in this case it's just however we are representing our derivatives. So that has a very real effect on how your solution will look like, whether it's stable, it's unstable, whether it will converge, diverge, these things. So for an advective system where there is a flow, the forward and backward difference schemes are stable. Okay, so from the earlier discussions and earlier classes, we have realized that the central differencing scheme is unstable for a wave equation kind of a situation. So basically, it's not suitable if you use the central differencing scheme, which is pretty easy, where you just take the influence of both the cells around the cell of interest and you go ahead and write your spatial derivative. But that doesn't work out well for advective type equations. So there are multiple ways to get around with that. This upwinding scheme is one of the one method. So basically, instead of using instead of using a central differencing method, we just scrap it completely and use a bias system, that is a forward or a backward difference scheme based on the direction of the flow to write down the derivatives. So this is the crux of the matter, and this is why we are looking at these different schemes. So quick scheme is one of those schemes which is using upwinding. Another information that I would like to give you for your future pursuits, maybe with development, is that it's not like you cannot use central differencing scheme with wave equations. You can definitely do that, but you will have to add some artificial dissipation. The concept of artificial dissipation is basically you modify your equation, like we were talking about modified governing equation earlier. So you modify that governing equation by adding some artificial dissipative terms, so that whatever instability the CDS, that is the central difference scheme, is introducing is going to be mitigated by that artificial diffusion term. So this is something that would be useful if you are planning on developing your codes. Otherwise, a quick scheme is a good idea, or just any upwinding scheme is generally more acceptable. It is very good at capturing shocks, because the CFD you sometimes want to analyze how the shock looks and etc. So these schemes, the upwind schemes, will give you a sharp shock interface instead of a blurry one. Meanwhile, the CDS will give you a blurry shock interface. This is simply a consequence of, again, the diffusive nature of the dissipation terms. That is, since they'll just average everything around a particular cell, so you'll just get a thicker band which will represent the shock and not a sharp one as you would get with these upwinding schemes. So this is something more development oriented, whatever I just talked about. Right. So then in this particular lectures this week, there was some importance of these factors, that is our ratio of upwind side gradient to downwind side gradient. This is all quick, particular to just upwinding schemes, right? And phi is the flux limiter function. So for in order for the scheme to work, we have to put this like there is a flux limiter function that is there, and that is intimately related with this r that we have over here, which is ratio of upwind side gradient to downwind side gradient, right? Okay, so I have a few questions. You should mostly be able to answer these on your own, and I will wait for your answers in the chat box. So let's read the question. So if a parameter R is defined as this, this is basically the same definition that we had taken earlier. That is, R is the flux of the upwind side, that is the definition. Upwind side gradient to downwind side gradient. So this is essentially the same thing, but it has just been represented in terms of finite difference of the property phi. So this phi is the property. Right. So in this case, what it is asking us, if a parameter R is defined as this quantity for quick scheme, the flux limiter function is defined as. So this was given in the lectures. So I'm waiting for an answer in the chat box. Right, that's true. Varuni and Deepesh have the right answer, that is A. So this is simply a matter of definition, nothing very technical about it. Of course, the derivation for to get to here is fairly long and complicated, and that for that I think very good explanation has been given in the lectures already. So we'll move on to the next question. In the quick scheme, the value of phi at the cell interface E of a control volume P is approximated as follows for f is greater than 0. So in this case, we are doing some upwinding over here where f is greater than 0. So what is the answer for this? So the answer for this is also given in your lecture material, wherein sir has explained that which side, like how the representation looks like of the value phi at the cell interface looks like when we have either of the yeah, Divyendu, that's right, it's D. When f equals to 0 versus when f is less than 0, we are going to have different treatments based on how much effect we are getting from either of the sides of our mesh, or where how much effect that location is going to have from either side. So this is also given in your lecture detailing. So it's fairly, this is a fairly theoretical topic generally, and there is no there's not much space for interpretation. I'm just spelling it out in words whatever we mean. So essentially this is just showing that when f is greater than 0, then how much is the effect of the left hand side versus the right hand side on the um, interface, right? Okay, so next again, this is something that was already mentioned in the lectures where we are talking about Swabi's range of possible second order TVD schemes. So then for these TVD schemes to work, that is second order TVD schemes to work, there has to be a particular relationship between the flux limiter function and the ratio of the upwind versus the downwind gradients. So over here I have, it's a similar diagram to what you might have seen in your lectures. That is, over here we have this green region that I have marked is representing the regions in which this second order TVD schemes are possible. So based on this diagram and based on whatever you have read already, so which of these like what is the range in which second order TVD schemes are possible? So just have a look at the diagram and then maybe just tell me which of the options which are right. A is one correct option. There is another correct option. Nandi, that's right. But tell me one more correct option. Just have it in case you're not if you're not completely confident with the material that was given in the week 7 PPTs. Just look at, yeah, great Nandini, that's fine. That's C, A and C. So these are two correct options. Now unfortunately these are all the questions that I have today. So what, I'll just speak a little bit maybe on the practical considerations of building a CFD solver in case you are interested in that. If you have any other occupations and you would rather use this time for something else, you are free to leave as well. If you want me to discuss about some practical considerations with respect to CFD solvers, I would be more than happy to discuss. I don't have such a problem over here, actually, Priyandu. And I'm not sure whether I have seen that material also right now. So I had a very limited set of material to cover today. Let me see if I can advective flux approximation as hybrid. Okay. So just give me a minute. Let me have a look at whether I have something like that. So is this something that is given in the lectures? An example or something? Let me see. I'll have a look and I'll come back over here. Give me around 5 to 10 minutes. I'll just figure out where this material is so that I might be able to help you with it. So I'm just going to open up the lectures. So let me know where I just downloaded the lecture material. So let me know which part we are talking about. So you're saying where you are using the interpolation. This side sort of a diagram where you're using, but for like multiple points, right? This okay. See, let's have a look. The hybrid differencing scheme of Spalding is based on a combination of central and upwind differencing schemes. Okay, just outline that. Central and upwind differencing schemes. The central differencing scheme, which is second order accurate, is employed for small Becquerel numbers. Yeah, okay. So we see why that is happening. That is happening because for small Becquerel numbers, diffusion is more dominant. And is employed for small Becquerel numbers, and the upwind scheme, which is a first order accurate but accounts for transportiveness, is employed for large Becquerel numbers. In this scheme, diffusion is set to 0 when P exceeds 2. The hybrid differencing scheme uses piecewise formulae based on local Becquerel number to evaluate the net flux through each control volume phase. The Becquerel number is evaluated at the phase of the control volume or a west phase. So this is what you're talking about, right? Okay. So in this case, I haven't gone through this right now, but I'm just going to study this with you right now. So basically, we see that for a particular situation, based on the Pecklet number, different phenomena are more dominant than the others. So if the diffusion is more dominant, then we are going to go with the CDS scheme. If the transportiveness or the advection is more dominant, then we are going to go with the quick scheme or any upwinding scheme. Which scheme are we talking about over here? Upwind scheme, yes. Right. Okay. So then basically you have a sort of a piecewise formula over here. Piecewise just basically means that when you have different um, conditions, you use different formulae to compute the same thing. So yes. So then you want me to determine AE and AW. That is various fluxes based on the um, on what I have over here. Here. This is the west cell. This is the current cell. This is the west phase. So if you have to compute the flux on a certain phase, then what you would do is that you would take the west phase's value, that is over here. That is what you need, right? What do you want over here? Divyanka, do you have a question in mind? Which is preferably not from the like, maybe you can give one of the questions in your assignment and I can have a look and sort of see how to solve it. I won't be solving it actually because we're not supposed to do that, but maybe I could just have a look at it. You can post it in this forum or something because I'm finding it difficult to um, know what to tell you from this. Please start from with exponential scale. Okay. Right, right. I'm trying to have a look at what this is. And then the west face is the east face. This is the current cell, west cell, east cell. Between P and E. Okay. Solution. I'm sorry, I just don't have enough background for this right now. I think here we use this exact solution in both left hand and right hand side. I am really sorry, but I really don't have any background for this right now, and I haven't seen this before really, so I'm unable to help right now. Um, let's see. You want an example for this, right? Let me look up an example if there's an example for this. So you're saying use both the right hand side as well as the left hand side exact solution at the faces, right, at the boundary faces, and then we go ahead and build the solution over that. So it would be ideal if I had a question like that and I could resolve that, right? So this particular lecture in which this example is giving, that was unclear, because I don't have any background on this and I do not want to confuse you further by winging it. Right. I think I'll have to ask the professor to take it up, or I'll have to consult with the professor on this topic. I'm sorry, I don't have a background on it. Um, I'll ask the other TA if he can help you out with it. Did you attend the Friday session? And if there was some background, like if there was some information on this particular topic for that, then maybe you could refer to that video. Right. For the Friday session, I think the TA over there had taken such problems. So it would be better if you just have a look at his video. I'll post the link for his YouTube channel in case you don't have that. So in there exactly this. Oh, unfortunately, I did not have anything like that in my portion for today. I am sorry. I'll just discuss with him and maybe I'll get back. Um, I'll get back on this. I'll be discussing this with you in a bit. I don't have anything else to say for now. Then, if this is the only question that is coming up from whatever we discussed, which is very minimal for today, then we can finish this class right now. Bindu, I'll try to work on it right now and give you an answer. So I'll get back. I'm sorry for the misgiving. Okay. Okay, then I'm finishing the class for now. I'll attempt to write down whatever is the doubt from here, that is on hybrid schemes, but I will have to go through the lecture on my own and then proceed it. So it might take me a few days. So I'll get to it as soon as I can. Um, I don't have anything else to say for today. So from my end, the class is closed. Um, I'll address this. Yeah.